Okay. Is this one working? It is. Okay. Hello, everyone. So my name is Amy Archer. I'm the vice chair of the Friends of the Dominion Astrophysical Observatory, and I'm very happy to welcome you to the center of the universe, or welcome you back if you have been here before. We're always happy when people come to visit us again and again. Tonight is a wonderful night to be here on Wasaysanych, which is the name the Indigenous people have called Little Saanich Mountain since time immemorial. I'm very excited to introduce our speaker tonight, Jaimie Greasley. Jaimie is a PhD candidate at the University of Victoria, and she's an expert in a field that sounds a little like science fiction, but is a very real, quantum computing. She spent her career studying everything from X-ray crystallography. Thank you. To machine learning, and she's going to help us understand how something as weird as quantum physics is completely changing our world. So her talk tonight is titled Think Quantum, What You Need to Know About the Quantum Revolution in 2025. It's no coincidence that the UN has named 2025 the International Year of Quantum Science and Technology, and Jaimie is here to help us unravel what that means for all of us. I will put in a little of my own 2 cents, which is that Jaimie and I met each other at an event when she said, I can teach you about quantum physics. And I said, oh, don't bother. There is no chance you can teach me about quantum physics. And within 5 minutes of Jaimie chatting with me, I was like, oh my gosh, I think I understand what you're saying. And so it was amazing, and I just couldn't wait to invite her up here so that she could teach all of us a little something. So without further ado, please welcome Jaimie Greasley.
All right. Wow, what an introduction. Thank you very much, Amy. All right, so I know that some might say that we're in the middle of the AI revolution, and that's true, that's very, very true. But today we're going to talk about quantum. Okay, so how I've structured this talk is that the first part of the talk is going to be the old news. Okay, so if you've ever taken an undergrad quantum physics course, then I'm here to refresh your mind a bit on that very first class that we take when we do quantum physics. We talk about the history of quantum physics. And then for the second part of the talk, I'm going to tell you the new news. So these are the recent developments or things that we've been coming to understand. And it's okay. So this is for all of us. And if you're just curious, then welcome. And yeah, so. Okay, so for those of you who may or may not know, 2025 has been declared the International Year of Quantum Science and Technology by the United Nations. So what this means is that we are in celebration of 100 years since the formulation of quantum mechanics. So back in 1925 to 1927, a bunch of prominent scientists you may or may not recognize, a few of them, this one, and this one, Marie Curie, and there are a few others. They basically developed the mathematical theory that would describe how nature behaves at its smallest level. So this is the level of atoms and light and molecules. But of course, as it would be, is that in developing this theory, they disagreed with what it would mean. But we'll talk about that later. So the best way to start this discussion is to talk about light. So the idea that light was a particle first originated in like the 1500s, where this guy, Gassendi, he thought things like light and heat, they were particles that traveled, okay? Newton sort of agreed with him, seconded that in the next century, and his reason was that, well, waves, they bend, but light seems to to travel pretty straight. So his reason was then, that light must be a particle since it travels in straight lines. But by the next century, and for the next 200 years or so, we would come to understand that light is actually a wave. And to support this, we had electromagnetic theory that said that, okay, phenomena like reflection, when light passes through a medium and hits a boundary, or when light passes around a corner, what happens? That was perfectly described by the idea that waves would superpose, and in encountering certain boundaries, how they would change. So that was readily accepted in the mid-1800s. Now, the picture was not complete. Okay, so there was this idea that when a body was heated, that it would start to give off radiation. And that radiation would present itself in a continuous spectrum. Now, classical theory, electromagnetism, did not fully explain this. And so Planck, at the turn of the 20th century, he said that, well, to fix this, we will say that energy is only exchanged in certain small amounts or discrete amounts. And he called that quanta. And that was the birth of what we call the Planck constant that helped us to see this small amount that was exchanged, or any energy was in this multiple of that small amount. So this was his last resort, though. So he funnily enough, he said that him giving into this idea to describe this phenomenon was an act of despair. Okay, and then by 1905, Albert Einstein had used Planck's idea of quanta, a small amount of something, to describe the photoelectric effect, which he went on to win the Nobel Prize for. But we understand now that whilst there was clear evidence for the wave-like nature of light, there was also evidence for the particle-like nature of light. And by the 20th century, what we saw was that electromagnetic energy was quantized, light itself was quantized, but there were other properties about these small objects that were also quantized. So charge was quantized. You could have only the smallest amount of charge is the charge of an electron. Okay, and any other charge that something might have is some multiple of that small amount. Atomic orbits was quantized, which led to Niels Bohr coming up with his model of the atom. But things like spin, which was kind of hard to explain at the time, it was a measure of magnetism, right? Those things were also quantized. So we had evidence that light behaved wave-like. Light was also particulate, but then by 1924, to this period, 1927, the idea came in that not only did light behave like both wave-like and particle-like, but matter could also behave like waves. And so this was the birth of wave-particle duality. And you can see from this experiment here, if you shine an electron through a barrier that has two slits in it, then the electrons will behave like waves, and they would spread out as they pass through the slits, and they would interact with themselves, giving birth to that interference pattern, which was strictly associated with waves. So back to this picture now. Using the collection of observations on certain experiments like this, they started to formulate mathematically what that means. And that language gave birth to things like the Schrödinger equation and a bunch of complicated things that became quantum physics. Okay, they described light and matter as both these wave functions. So the state of light and matter these wave functions, and these wave functions evolve according to the Schrödinger's equations. But not only that, there were some really strange things that happened when we, for example, took measurements or we try to observe these systems. And so we'll start with Schrödinger's cat. So what they observed is that if a quantum object could be in superposition, just like waves, it meant that if I had a cat, sorry, you see my part. If I had a cat, then this cat is a quantum cat, okay? It meant that if I had this cat in superposition, I'm not observing it, it's sort of going between these two states, both alive and dead. But the minute that I decide to observe it, it chooses a reality. Sorry, I'll get in trouble with that word. It probabilistically falls into an outcome that we can understand. And by repeating this experiment, so we prepare the same quantum cat in the same way, we repeat the experiment, what we find is that it chooses an outcome. And so what happens is that when you repeat this experiment multiple times, you get some probabilities of outcomes. And those probabilities kind of tell you a bit about what was happening before observation. Now, how real is this? It doesn't sound quite real, and several people had a problem with it. Notably, one other thing that happened was the topic of entanglement, which said that now we have two quantum cats. Okay, so these quantum cats have interacted at some point in time, and due to their interaction, okay, they became entangled. So they have some sort of special correlation between them that we don't particularly know how to explain. But if you were to separate these quantum cats and send them off to the opposite ends of the universe, what will happen is that when you look or measure them simultaneously, so you have an observer here and an observer here, right? What will happen? They would always have some sort of correlated outcome. Now, this was strange. Einstein had a problem with this. Why? Because we made some assumptions. The first was that when we don't know what the outcome is going to be until we measure or we observe the system, and that if we were to measure and the objects were separated by space, then how would one know how to be correlated to the other without some sort of faster than light communication? And this was in direct contradiction to what he had proposed, that nothing, not even information cannot travel faster than the speed of light. So he had a problem with this. And so he suggested that, well, there's a problem here, and it meant that he thought that quantum theory was not complete. Mathematically, it described things perfectly, but maybe there were some sort of hidden elements that influenced these measurements at that time. And he said that it was in contradiction to what we say local realism. So the question came, is the universe locally real? And what we mean by that is, real means that no matter if we observe it, that there is still some sort of objective reality to what the property of that object is going to be without observation, right? And locality meant that measurements, things like measurements, were only influenced by its nearest neighbors and not by something that was separated. So for such a question, John Bell, he came up with these formulae that basically said that, well, if quantum theory is real, if any local theory is correct, sorry, any local theory is correct, then there would be some violation. There would be, sorry.
I'm not sure what you're trying to edit.
Very disruptive. Okay. So John Bell basically said that for the truth of the matter, if quantum mechanics was wrong, or if quantum mechanics was correct, there would be some violation of inequalities, essentially. And if there were some hidden variables, then we will see certain correlations that would not be violated when we took measurements in these experiments. And for such a question as that, we come to that the answer is that the universe is not locally real. And this is after many, many years. It's very hard to conceptualize what that means. But the answers to this question were given by 3 people who, in 2022, they won the Nobel Prize in Physics. And it was for experiments using entangled particles of light that demonstrated that there were always these super strong correlations that did not match any local realism. So they constantly violated Bell's inequalities. So that's the first part. And you might say that, okay, what does it all mean if the universe is not locally real? I'm here to tell you that the common viewpoint that we take is this, which was David Merman. He said, shut up and calculate, means that we don't really know or understand fully at this point how to interpret what quantum mechanics means, but we know what we can do with it. So you might know that quantum technology is already in existence. Okay, so from lasers to atomic clocks for GPS, for your phones, you have transistors, semiconductors, in magnetic resonance imaging, they all make use of some quantum effects in order to function. But since we're talking about the second quantum revolution, what this is essentially is being able to control these quantum systems in a way that is way more fine-tuned than what we would have with these technologies. And the example I'm going to give you is quantum computing. So classical computing, we know, involves the processing of bits. So you have a set of zeros and ones, which can be the voltage levels in transistors in your computer. And we do some set of logical operations on these bits. So it's basically electrical circuits. And through those operations, we get some output. So we get an output bit string. It involves taking some input, doing processing, and giving some output. But quantum computers, instead of manipulating information that way, they manipulate quantum information. And the most basic units of quantum information is what we call the quantum bit or the qubit. So just as quantum mechanical systems can have properties such as superposition, interference, entanglement, well, these qubits can also demonstrate those behaviors. So instead of just 0 and 1, we have some mix between 0 and 1. And this, we say, would offer some sort of higher dimension to computing, especially when it comes to complicated problems. So real examples of qubits would be trapped ions, particles of light, or small superconducting circuits that essentially behave as artificial atoms in that they demonstrate quantization. Okay, but what does quantum advantage mean? We expect that it's going to be better than classical computing, but what that means is that we want for quantum computers to be able to run something more accurately, more cheaply, or efficiently than a classical computer. And it achieves that probably through quantum superposition. For example, this is a quantum circuit. And what we've done here is that we have some qubits that we've each placed into superposition. Now, if we were to measure at the end of the quantum circuit, what we will see is that all the possible outcomes of bit strings, zeros and ones, are likely. So is this a new form of parallel computation? And if you think about that, it means that we can definitely process a lot more if we can do all inputs all at once. In addition to this, we have entanglement, which allows us to have certain correlations between qubits that are not necessarily classical. They can't be done on any classical computer. So maybe these can speed up certain types of computations. And the best examples we have of this quantum computing being really effective is actually Shaw's algorithm, which in 1994 was able to use superposition and things like interference in order to show that we can factorize large prime numbers and could potentially break RSA encryption. Now, this was theoretical, okay? So we haven't demonstrated this in any real way other than to factorize 15, okay, which is 3 and 5. Another important algorithm was Grover's algorithm for searching through some sort of database. So if you have a large database and you need to find a result. So he again used superposition and a bunch of tricks like interference and so on to be able to get an outcome with high probability that's the marked entry in a database. But does that mean that because we can compress our information exponentially, does that mean that we get exponential speed up in our computations? And the answer is not necessarily. So quantum superposition does not guarantee exponential speed up, okay? And but even some of the best algorithms show that any amount of speed up, not any amount, but can show good speed up for certain problems that we know will just not be feasible for classical computers. So what does it take to scale up hardware? Well, we have to understand that qubits are very sensitive. They're sensitive to the environment, they're sensitive to noise, they're sensitive to radiation, sometimes temperature, okay? And so in order to do any type of computation, we need these qubits to interact, either with themselves, with the environment, and that's how we run a computation. But if they interact too much, then what happens is that they collapse, they start to lose their quantumness in essence. So it is an engineering challenge to build up these real world problem solving quantum computers, but we have seen a lot of progress in the last 2 years or so, just as AI has, actually. And we expect that we will be able to solve some really important problems in many, many industries. So from materials design to drug discovery, climate change, banking, AI even. But it's going to take some time. And to support these efforts, the National Quantum Strategy has been developed by Canada, which invests towards quantum research, talent, and commercialization. In fact, the NRC found that in about 20 to 25 years or so, there will be 200,000 jobs associated with quantum technologies. So we are in for a lot, and there's a lot of progress to be made, but I think we are on our way there. So thank you. Yeah. Yes.
AI and quantum. So AI isn't dependent on quantum right now.
No.
But the